Okay, that's what you get from teaching first-year physics for what, 5 years? In Australia, like in the Philippines, a lot of years as well. Okay, so beam splitter, very common device if you're an experimentalist. There are two input ports. We label them here S and I because usually the input is signal and idler photons. So let's just call them S and I. They have different properties, can have different color, different polarization, different time when they enter the beam splitter. But what this paper shows you is that if all those properties are indistinguishable, if the two photons are indistinguishable, like there's no way you can tell them apart, what will happen is that the two photons will bunch, meaning they all come to only one detector, okay? And I know I'm like making the photons look like humans, like they're choosing which port they are going to go out of. But I promise you it comes out of physics as well, okay? So the experiment is you have indistinguishable photons, but you're changing the time delay of one photon. So they're not arriving at the same time. And then there will be a time when they will arrive at the same time, and there you will see the bunching behavior. So this is a coincidence count. So if I'm going to plot that, a coincidence count, you're just asking yourself, is there a click on both detectors? Okay, so the signature Hong-Ou-Mandel dip is this. This is the coincidences. So that's the signal that you get from these two detectors. Do both detectors click? When they both click, meaning one photon chose to go one detector, the other photon chose to go the other detector, right? When you get to the point where the photons become indistinguishable, they arrive at the same time, their polarization is the same, frequency is the same, spatial modes the same, they will bunch, they will come either to this detector or this detector, both of them. So you lose the coincidences, okay? You get this signature dip around this point here, where we call it the zero delay because the two photons arrived at the same time. There is some width associated with it, and that width is, a function of the filtering that you use and, other factors in the experiment. But the important bit to take away is that there is a point where they are bunching. There are no coincidences, okay? That's the Hong-Ou-Mandel dip. Yes?
We heard water.
Oh, okay. Water.
Outside, it's raining outside.
Oh, okay. Oh. Okay. So Hong-Ou-Mandel dip. It's very, it's a very nice quantum phenomenon. This is the quintessential quantum optics phenomenon. You cannot describe this without quantization. Okay, so even Willis Lamb will agree that I can call it a photon when it's in a Hong-Ou-Mandel experiment because I actually need quantization for it. Okay, John Rarity, we've heard his name a lot of times this school. He wrote a very nice article reflecting on the Hong-Ou-Mandel dip. He called it the not quite Loudon-Fern rarity tapster dip. The story is that Rodney Loudon actually discovered the Hong-Ou-Mandel dip. He didn't call it Hong-Ou-Mandel dip, but he discovered this phenomenon of the dip in the coincidences a bit earlier actually than Hong-Ou-Mandel. And well, when I heard John talk about it, like he said, okay, Rodney talked to Tapster because John is not really the listening kind. I'm not sure. Oh, this is recorded. So anyway, so he said, okay, and they didn't actually pay as much attention as maybe you would have. And then a few months later, the Hong-Ou-Mandel dip paper came out. And then when it came out, like, oh, that's what Rodney was talking about. So it's the not quite Loudon-Fern rarity tapster dip. But that's just an aside. So just to say that we have to credit Loudon as well, because it's an optics communication paper that I think was a bit earlier than the Hong Amandel PRL paper. What is undeniable is that Hong Amandel is very important for quantum optics. If you're doing photonic quantum computing, this is like bread and butter. So I wanna start with some operators, and I'm sorry I have to show you this. I actually just got a screenshot of John's paper. So we define just the operator. So this means that this is a creation operator. If you have an input vacuum, so there's no photon here. So I'm changing gears, by the way. This is the 0 and 1 is a number basis. So 0 photon, 1 photon. You apply a creation operator to 0 photon, you create 1 photon. And then you have a subscript I here to denote some mode of the photon. Okay? Creation operator. There is also the annihilation operator, which destroys the photon. So if you apply annihilation to a Fock state 1, it becomes a 0. And they follow this nice commutation relation. Okay? So this is a beam splitter. And it's funny preparing for this lecture. Gerard Milburn actually gave me his slides for his quantum optics course because I'm teaching it this semester. And I thought, okay, I'm gonna steal Gerard's slides for the Hong Amandel derivation. And ooh, that is like 3 slides for Hong Amandel interference. So I said, let's see what John thinks. And here I have you here in 3 lines, okay? But if you want a fuller treatment of it, like you can go to any quantum optics book. But this is the gist, okay? You have.
Give you some history, okay?
Yes.
I first saw the slide in version 0 of the book Milburn and Walls in 1988.
1988.
So
Also,
it's a very old set of stuff.
Yes. It's got the use in it. Yep. Still, yeah. So anyway, so I think this one appeals to me more as an experimentalist. So what happens is you have an input here to this is the beam splitter. You have 2 input modes, 2 input photons. So that's why 1 photon in 1 mode, 1 photon in 2 modes. So it's just the path here, which just as a result of applying your creation operator. So you get this one. And then now this beam splitter acts on this input state. And what happens is some of the times the photon will go to path to mode 3 and sometimes to mode 4. Okay? This is an experimentalist beam splitter, so I have eyes there. So you have transmission, reflection for, oh, sorry, what happened? Okay. So you got for A1, it has the probability of getting transmitted, getting reflected. For A2, it also has probability of getting transmitted or reflected, and that's just defined by the beam splitter relation here. Okay? So now when you write this as the output, of course they are like independent events, so we just take the product and you work out with some simple algebra. What turns out is really something beautiful in that one of the terms actually has this t squared minus r squared defined by your transmission and reflection. And if t equals r, this term will disappear. And you only have the possibility of detecting 2 photons in mode 3, where 1 detector is, or 2 photons in another detector here. Okay? So you see the Hong Amandel comes from just applying this quantization to the photons. Okay? And experimentally, that's great because it's an easy experiment to show. You need indistinguishable photons, you do coincidence detection on your 2 detectors here. And it's very important in a lot of linear optical quantum computing. Okay? So if you ask me when did photonic quantum computing start, I will really say it's the Hong-Omandel paper from the 1980s. We didn't realize it was important for photonic quantum computing, but without it, photonic quantum computing will not happen. Okay? So now I'll go through, as I've said, this is going to be, I will not go for 2 hours, definitely. I'll just show you what has happened since Hong-Omandel. But first, what do we need for a photonic quantum computer? You need single qubit gates or single qubit gates. Like I do think of them as like just unitary operations. And this is one paper from Zeilinger. People often call this the Rick and Zeilinger decomposition, but there are other authors here. Why don't we use their names as well? Anyway, so when people say Rick Zeilinger decomposition, it just means given a unitary, I'm going to decompose it in terms of beam splitters and phase shifters in a Mach-Zehnder configuration like this. Like remember Arthur's Mach-Zehnder where he has like the mirrors and phase shifters. And so this paper tells you any unitary, so any single qubit, you can implement it using a network of beam splitters and phase shifters. Okay? So that's single qubit gate. So that was not the problem. The problem with photonic quantum computing is that the photon doesn't interact with other photons. So it's not quite like matter qubits where it's easy for one spin qubit to affect the other spin qubit. Like, I don't know, maybe you put them close together or do your control trick. Photons do not interact with each other. That's why it's great for measuring entangled states and maintaining coherence and all that. That is a double-edged sword. It means you cannot do two photon gates easily. Until Neil Laflamme and Milburn in 2001, they discovered linear optical quantum they have a linear optical implementation of a 2-qubit gate. Okay, and I don't think I put the diagram here, but it's honestly it's hard to understand. Okay, so my tip for you is read the experiment paper, which has got Tim Ralph and Andrew and Jeremy O'Brien in it. That is easier to understand. But the summary is that if you allow your 2-qubit operation to fail, again, because it's life, we can fail. If you can allow for failure, you will be able to do a 2-qubit gate. So they actually did a C0 gate with a success rate of, was it 1/9 or 1/16? Something. 1/16. 1/16 success rate. So this was the theory paper. There was an experiment paper from Jeremy O'Brien and Tim Ralph. Read the experiment paper. Okay, so that's when linear optical quantum computing really started. I don't know if do you know Valerio Scarani from NUS? He actually hates photonic quantum computing. It's the most stupid thing ever. And I can understand that because it's actually very hard to do these 2-qubit operations in photons. But what it allows you to do is you can mass produce these sources, as we know now. Because if you're doing things probabilistically, you need a lot of shots in order to succeed in a practical way. Okay, like if you read nowadays we have papers that do entangling of qubits. Not a lot, maybe I've seen 1 or 2, and the success rate is even lower. So you need to somehow mass produce these photons and try a lot of times. And the only way that you can do that is to go on chip, right? I'm not gonna cascade 100 BBO crystals, regardless of how efficient they are. It's gonna be hard. That's why we have to go on chip, and that's what PsiQuantum is doing. So that improves scalability and efficiency. It improves stability. Like if you've ever worked on bulk experiments, it's aligning and aligning again. And then you have that 1 or 2 days where everything's perfect. You take your data. Maybe you do it again if it's not so convincing, but it's a lot of time spent on, doing these things. So going on chip improves your success rate. It brings quantum photonics closer to applications. There's actually a nice roadmap from the Galan, Moody. I think Bill has a paper. You have a paper on this, right? Yeah, so we there's a quantum photonics roadmap. If you're interested, you can check that out. It talks about the different platforms, different degrees of freedom, and some challenges as well in each of these platforms.
Some challenges?
A lot of challenges. Okay, so we have Hong-Ou-Mandel that we use. So Hong-Ou-Mandel was important to get the 2-qubit linear optical gates, and there was a lot more development in between, but I'll leave you to explore that. This is where we are now for photonic quantum computing. I think there are, I don't know. When we talk about photonic quantum computing, it's usually fusion-based quantum computation. And what that means is you have a lot of photons. Each of these is a photon, and then you have a fusion network. You're doing Bell fusion, meaning you're entangling this through your Bell measurement. So there's a lot of those that you need to do in order to make your resource states that you consume entanglement every time as the computation moves along, you're consuming the entanglement. So you have to make a lot of resource states. So often, when people ask, what is the gate time for a photonic quantum computer? What's the gate time for a photonic quantum computer? Like for a matter qubit, like for an ion, for example, maybe you apply some pulse, it will relax with some well-defined time. For photons, it's kind of hard actually to say what is the gate time for a photonic quantum computer, because as Bill said, it's performing the computation at light speed. But it has a lot to do with the rate that you are generating your resource states. So how quickly are you making your indistinguishable photons? Like the indistinguishable part is very important because your entangling operations are relying on Hong-Ou-Mandel interference. So you need indistinguishable photons. You need to make lots of them. You need to make these entangling operations in your fusion network, and somehow you have to make them in such a way that it's practical for your computation. You're doing it at a rate that's useful for the computation you're trying to do. So you see how challenging it is. It's really hard to. It's a difficult, to me. It's a difficult model of computing. The benefit really is that you can mass produce something like this, because especially if you do it in silicon, we do a lot of things in silicon, right? So I am hopeful, but I know it's also hard. So this paper, so this paper has a supplemental material, which is also very dense, but I just put here, each of these things here is the Bell fusion operation, and you can flag whether you have succeeded in that operation or you did not. So that's important because you need to be able to, I guess, know what resource states you're doing and when you've succeeded to do it or not. So, okay, but it's very probabilistic. Now, loss in that paper, they probably have better loss thresholds now, but they tried on different codes. Like, I'm not an expert. I'm just showing you the plot that they have for different resource states, and the probability on the y-axis, photon loss threshold, this is fusion failure probability, okay? Like if you're an experimentalist, you look at this and these are very small losses. It's kind of, so in order for, say for example, okay, say sure, this one, okay, let's just say I want it to succeed 80% of the time, okay, that's where 0.2 is, okay? That means my loss has to be around 2% for the entire thing, okay? So, well, like, well, if I try hard enough with my bulk optics, I couple about the fiber, like maybe, okay, I'll get to the 80s, 70s on a really good day. So it's hard, it's challenging. But they are actually, I think, moving in the right direction, and they have some really cool stuff. If you haven't seen this paper and you're a photonic person, you should read this paper. It was on the archive for a long time and then came out in Nature just this year, a manufacturable platform for photonic quantum computing. They have really, really good results, which of course they will not share with, they will not maybe sell to academics like me, but it's very cool. So what do they have in that paper? They have Hong-Umandel dips from photons from independent sources that is at 99.5% visibility. Like, that's really good. And then they have qubit fusion measurements. So how close are they to entangling those two photons? So this is like fidelity to the entangled state. That's 99.2%. Okay? Spam error, so preparation and measurement error, like all above 99.6%, is that? It's just really, I was drooling reading this paper. And it was all enabled because they have a really good, they spent a lot of time they invested a lot on the platform. So this one, for those who know what a joint spectral intensity measurement is, so this is something, when you have spontaneous four-wave mixing, you're creating your two photons. The wavelength will be defined by the phase matching of your spontaneous four-wave mixing. For it to have really good special purity, you want them to be separable, right? So what you don't want to see is a correlation on the diagonal. Like, this is frequency of signal, frequency of idler. If it's a blob, it's good, meaning you have a good spectral purity. You can use it for your Hong-Umandel interferences. This is a good source of indistinguishable photons from independent spontaneous four-wave mixing sources. So you measure joint spectral intensity for each of these sources. You want to make sure that they all look like this, okay? And then they also have a very good photon, they also have the detector on chip. I forgot what the material is, but like the efficiency is also super, super good. I think they're like the most value for money investment that they did was actually working on BTO. So BTO is a phase shifter. When Jeremy and friends in Bristol were doing linear optics in the early 2000s, like I mean up to the 2010s maybe. So you need a phase shifter that's usually a thermo-optic phase shifter. You actually heat. So what we know about physics, you have index of refraction. If you change the index of refraction, you will introduce a phase delay to the photon. How do you change the index of refraction? You can heat up your waveguide. When you heat up your waveguide, index of refraction changes, you introduce a delay. The problem with that is, one, you have to heat up, so it's a bit energy expensive. You actually have to cool your chip because it will heat up. And it's not quick because you have to wait for the waveguide to heat up and then relax again. Like it's not quick. BTO, if you're familiar with lithium niobate as a material, it's got an electro-optic It's electro-optic rather than thermo-optic. So you can control it very quickly, and it's got better nonlinear properties than lithium niobate as well. So PsiQuantum spent a lot of money on actually perfecting the process for BTO so they can make BTO wafers and make these BTO modulators. Okay? As I tell my photonics colleagues, even if they don't make a photonic quantum computer, I think they'll make a killing from the BTO. See, Bill agrees. Okay? So as they have all the ingredients that they need for a photonic quantum computer. It is a matter of really beating the loss thresholds, which I think is still hard, but I think they're on the right track. Okay, now it will be a disservice to this other company to not talk about them. So Quandela is another photonic quantum computing company. So these are all DV, by the way, like discrete variable. I'm sure Valentina next week will talk about Xanadu. Xanadu is also another photonic quantum computing company that uses continuous variables. And they also have on-chip, they also had a recent Nature paper where they have things on-chip as well. So maybe Valentina will talk about it. Quandela, so Pascal, like I'm conscious I keep on showing pictures of men. So I'm going to show you a picture of a woman. So that's Pascal. She actually is I don't know, condensed matter kind of person. So she makes really good quantum dots. And there are other companies that does quantum dot, like Sparrow and all that. But quantum dots is another source of your indistinguishable photons. So remember, in PsiQuantum's architecture, they are using spontaneous four-wave mixing sources. So you're making the two photons in a spontaneous way. So it's probabilistic. The way you generate your single photons was probabilistic from the start. Quantum dots, you can pump a quantum dot, and it's very likely there's going to be a single. Okay, so the beauty of it is that your process for generating the single photon has a higher efficiency in a way. Okay, the problem with it is I don't think it's as manufacturable as spontaneous four-wave mixing. Like you make your quantum dots in your substrate, and you actually you need to find the quantum dots, characterize the quantum dots, and tune them in a way that you make really good indistinguishable photons. But they have very good quantum dots, and they're doing more photonic quantum computing these days as well. So I'm excited by that company too. In particular, they have this not recently, but like in December, they put out this paper where they also do fusion-based quantum computing, but they do it with hybrid spin photons, because quantum dot is a nice condensed matter. It's that artificial atom, right? So you can have spin there as well. It emits a photon. So they do some coupling between the spin and the photon, and they claim in this paper that you can minimize the resource overhead if you do it this way. And I think I visited them in February. They said it's like orders of magnitude, which if would be good. So check that out as well. They also have a platform called Percival. If you want to play around with some photonic quantum computing circuits, Percival is really nice to just play with some things. I think PsiQuantum released just last week Construct. Do you have access to Construct? Yeah, I looked at the form. I tried to fill it out, but I didn't have time to finish it. There are some questions that you need to answer. But Percival, you can just access. It's free, no questions asked. Actually, I have students who play with it. Okay, so that's where we are for photonic quantum computing. I think it's very exciting. PsiQuantum did promise the Australian government a photonic quantum computer in 5 years in Brisbane. They might do it, they might not do it. Like, I don't know, but it's photonic, so I'm happy. And I'm an investor because I pay my taxes in Australia. They got $1 billion from the Australian government. So yeah, I wait with much excitement. Okay. Okay, so this is the last part. I want to show you some results from my lab, like not very fresh, but we got them last year. But as the publishing process goes, it takes a lot of time to publish. But okay, I'm going to talk about some inverse design components for homomandal interference. Okay, so you would know by now my favorite QDIT is the transverse modes, because in free space it's really very convenient. You generate high dimensional entanglement in SPDC. You have very nice device called SLM that can do your processing for like the gates and the measurements as well. On chip, that's not quite, it's not as straightforward. So we have devices like this. So for example, this one is a device which will tell you which transverse mode the photon is. So it's a demultiplexer, sorry. I get confused. Oh, this is a demultiplexer, right? It's a demultiplexer for all these modes, okay? And the way that you design devices like this is to start from the ground, from the bottom, like from first principles, you know, with evanescent coupling, you can calculate which modes will go from this waveguide to this waveguide. And then you can vary the distances between the waveguides, the thickness of the waveguides, the bends of the waveguides. There's a lot of parameters that you can change and then simulate whether it's doing the multiplexing for you, okay? So it's a bit tedious to design from ground, from first principles to function, it's a bit tedious. Now, like you would have seen yesterday in my talk, like in my MPLC gate, what I do is I define what the input is and I define what the output is and I let an algorithm find me what the gate is. So I want to do the same for on-chip transverse modes. And luckily, there is something called photonic inverse design. So maybe you'll be familiar with this, like Yelena Vukovic's group started this photonic inverse design. It's really, really cool. I visited their group in 2019 before COVID, luckily. And they showed me spins. The devices look wild. So this device, for example, is a device that would sort two different wavelengths into these ports, okay? I cannot design a device that will look like this from first principles. Like I wouldn't be able to tell you, why do I have like a spade looking thing here, right? It looks wild. So the way that you do photonic inverse design is very much like MPLC. You design by specifying what you want the device to do. So I have a user-defined input and a function which some algorithm will take in order to find an optimal device. And there's a lot of work, so this is topological optimization. There's a lot of work which shows that they are more robust and they're usually much smaller than what you would otherwise design from the bottom-up approach. Okay? So it's a bit more convenient. It's more convenient than the traditional method of designing. Okay, so that was 2019, and then COVID happened, and I didn't get a student, so I supervised one remotely from the Philippines. So that's Jam. She started doing photonic inverse design for our group. It really is simply optimization. So you can you design, you give the device your function, and then from there it's electromagnetic theory, right? It's, you know, the equations that will move the field forward and backwards. You use some sophisticated gradient descent again. And the nice thing about it is because you're defining your cost function for you have a cost function that will define the function of the device, right? You can also set some fabrication constraints. So say, for example, I don't want the holes to be less than 100 nanometers. because I know that my electron beam lithography cannot do less than 100 nanometer diameters. You can set all those constraints in your cost function, okay? So it's also like, you know, I was talking about self-guided tomography as well yesterday. It's some gradient descent algorithm in this really big parameter space, okay? So we get the package. So I'm not an expert in adjoint optimization. We get a package that we just define what the input is and what's the output that we want, okay? So for example, here I have okay, I'm gonna do, what's this? Okay, so here, for example, I am just multiplexing two modes. So you've got single mode here, and then after this device, I want them to be TE0 and TE1. Okay, so I define functions for it, a cost function. For this one, I want to maximize transmission to the correct mode. I want to minimize transmission to the wrong mode. And then I let the algorithm find me the device that will fit in a 3x3 micron chip, a 3x3 micron silicon. The simulation area, you have to, of course, pad it with some other material. So usually simulation is, you know, double. And then we ran it, like this is for a laptop. I must say now, seeing how good it was, what I did was actually put spins on an HPC at UQ. So we now have a GPU cluster with spins in it. So if you want to do some wild devices, yeah, you can talk to me and maybe we can run it in an HPC. So for this device, this first device that we did, it was 8 hours for 100 iterations, 40 nanometer mesh, and the results were these. So again, I couldn't explain why this is the design, but it works. So as you can see, I have a mode here after traveling through this device, it's TE0. If there's single mode here, if there's TE0 here, after this device, it's gonna be TE1 here, okay? The way it does the optimization is at first, it lets the permittivity of the material be continuous, okay? So of course, when you're talking about silicon, there is only one correct index of refraction of silicon for a particular wavelength, right? But the computer doesn't know that. So we just let the permittivity to be continuous. You know, assign it anything that you like that will make this device work. So those are the continuous stages of the optimization. Okay, these are just the cost functions. I'm trying to optimize transmission, minimize crosstalk. And then after continuous optimizations, you discretize, okay? You can choose how many continuous stages you want. So you can tweak that. It's up to maybe the complexity of your device. We find that for our cases, most of the time, 2 continuous optimizations is fine. And then on the third one, we discretize. So like you apply some, not step function, but like some tanh function, so that you say above this number, you're gonna be silicon. Otherwise, you're air or silica or whatever is the material that we're gonna put there. So after those 3 stages of optimization for us, we get a device like this. We simulate it. And so SPINS has its own simulation of the modes there as well. We use tidy3D these days. Like, do you know tidy3D? It's a really good FDTD, really good. So tidy3D, you don't need to make your own FDTD, use tidy3D. It's got a nice graphic interface as well. So we simulate the device, we see that it works. We try several experiments, so we run it several times. We just see what solutions come out, because of course it's optimization, right? It can be, yeah, I don't know, like the solution will not be unique. In this case, we ran the same cost function, the same everything. You run it 3 different times, you get 3 different designs. like these ones. And then we fabricate them. So these are actual fabricated devices. And then we simulate their performance. You see, their performance actually is not too different from each other. So we just choose one that's good enough. We fabricate it, and then we test it. So that's mode multiplexer, because I want to measure what mode. The other thing I need is a mode beam splitter. So this is a beam splitter on chip. I have a TE0 going through this device. After that, it's going to be 50-50 in TE0 and TE1. It's a mode beam splitter. Okay, the device looks like this. This is the simulation. And we simulate it. It's not perfect, but yeah, we just fabricate it. Let's see what we get. Okay. So I have a multiplexer now and the beam splitter. It's kind of like my free space beam splitter. Like the free space beam splitter is like multiplexing on path, right? What I'm doing is like multiplexing on modes. So we designed a multiplexer and a beam splitter because we wanted to do Hong-O'Mandel interference on chip with using transverse modes. Okay, so let's review Hong-O'Mandel again. You've got the 4 possibilities. 2 of them cancel. So you get the Hong-O'Mandel interference where the photons are bunching. It's the same when you're talking about modes. So this is an example of a frequency beam splitter, where like you see, it's like path, except that now you have like frequencies instead. Okay, so what we're doing is a mode beam splitter rather than the frequency mode beam splitter. And it's not the first time that something like this has been shown on chip. So this is actually a Hong-O'Mandel experiment using transverse modes from Mohanty. Like it's a group in New York. I forgot the name. Anyway, you search it up. The beam splitter that they have here is a grating. So like if here the mode mixing here is on a grating. The whole length of the device is 170 microns. We thought we can make that smaller. So what we did was to put mode multiplexer, mode beam splitter, mode demultiplexer. We have a Hong-O'Mandel experiment with a 20 micron footprint. Okay, it will do exactly the same thing as the Mohanty experiment, except that we use inverse design components and it's smaller. So like it was exciting because you make devices like that look wild, and you have to ask yourself, will this work? Because as we know, quantum is a bit more, I guess things have to be a little bit more perfect in the quantum world than your usual classical world. So we thought, okay, let's do a Hong-O'Mandel experiment using these wild devices. And we wanted to test it to its limit. So we needed the best possible indistinguishable photons that we can get. And luckily, just across the river is Griffith University. They have very good indistinguishable 1550 nanometer photons. Like their Hong-O'Mandel visibilities are 99.something%. Okay, so we use their photons. So these are very indistinguishable photons. We put them through our Hong-O'Mandel interference on chip. And ta-da! That's the Hong-O'Mandel dip using the mode multiplexer and mode beam splitter that we have. Okay, so we get a visibility of 99.56%, which is actually, if you were to measure the indistinguishability of those photons, not with our chip, but just the usual Hong-O'Mandel experiment, it actually gets very close. And the nice thing about it is, because as we said, the promise of inverse design is it's a robust way of designing. like if you remember the 10 mode device earlier, it will be very sensitive to the exact width of the waveguide, to the exact distance of one waveguide to the next. It's gonna be very sensitive to those fabrication errors. So we said we are going to fabricate a few devices, and we tested the Hong Umandel dip in all those devices, and you see they all get really pretty close to 100%. And this is, I must say, without any tuning, Bill, without any tuning. Literally, you make copies of your device, you put photons, measure your Hong Umandel. In order to do something like that, say for path, for example, you would need thermo-optic phase shifters to make the photons really, to make the visibility really good. This is without tuning. So we're very happy about that. We can model also the visibility. We have one rogue device. I don't know what happened here, but the beam splitter quality wasn't very good, but it's still 80% visibility. We also simulated fabrication bias. So of course, when you go to your EBL, you hope for the best, but the EBL might on one good day, oh, I'm gonna put 5 nanometer bias, as in, I'm gonna make you a circle that's 5 nanometers bigger than what you want. So there are those things that you have to just struggle with as a fabrication person. Luckily, I don't fabricate things myself. There's a postdoc in the group doing that. But we simulated fabrication bias, and then we checked whether we can still go above the 50% threshold for Hong Umandel visibility, and we still get, even with 10 nanometer bias, we have 90% visibility. Okay? So that's the end of my session today. So I introduced Hong Umandel. Okay, Hong Umandel interference, or the Loudon-Tapster rarity like dip. It's the quintessential quantum optics phenomenon. You cannot get it without quantization. So it's very important from the quantum optics point of view, and also very much so for linear optical quantum computing. That's what we use for the non-linear part of the linear optics quantum computing. And I showed you some exciting developments towards fault-tolerant photonic quantum computing. Sorry, I should put photonic here. Photonic quantum computing. It's a very active field. I think this is a good time to join the cause. PsiQuantum invested $2 million in a company for quantum error correction, started by PhD students from the University of Sydney. Have you heard of this, Bill? Like, I think, oh, that's fantastic. So if you wanna join the cause, please. And then finally, I showed you some really cool results. I think they're cool. The inverse design components for quantum information processing. And I think, especially if you want to control modes, it doesn't have to be transverse modes, by the way. Like, I think, like you saw the wavelength multiplexer earlier, like you can do it for anything that you can write on your Maxwell's equation, you can use it for that. And I must say, like, I don't want you to think that I have given up on intuition. I have not. I trust physics. Because at the end of the day, it's physics equations back and forth. But I kind of think that the solutions that we are getting, because they're so wild looking, I'm beginning to think, is there a way actually that you can recast a problem like that in a way that these patterns become intuitive? I don't know. So what we've done recently is actually work with researchers from Singapore in NTU and NUS, like quantum machine learning people. So what we did actually was, I don't show the results here, But what we did was we inverse designed multiplexers, lots and lots of them. So we had like, I think it's not a lot from a machine learning point of view, because I think we had 500 designs for a multiplexer that all look a bit different. And then we manually, this is the hard part, we manually check the spectral response of each multiplexer. Because if you have a multiplexer, ideally you want it to work over broadband, right? Like say 100 nanometer broadband, say 200 nanometers. So we classified our device to the broadband, to the not broadband. So we have two labels for this set of 500 multiplexer designs, and they all look wild. We gave them to our machine learning friends, and then we said, okay, tell us which areas on average are important for the broadband characteristic. And then from there, like they highlight some areas, and then from their results, we started with an initial design that was supposedly gonna give us the broadband characteristic. So we started with an initial shape from the machine learning interpretability results, and we actually got really super flat spectral response. It's I cannot wait to fabricate those devices, Bill. I think the 5 dB or like the 5 dB bandwidth was like 200 nanometers. It's just unbelievable. So yeah, I am hopeful. Okay, that's all. I give you 2 hours of lunch break.
2.5.
2.5 hours, unless you have questions.
So first, let's think. We of course have questions, and I'll start with one. So with the inverse design, have you thought about, if you get many designs out, have you started thinking about putting get out the many designs, start putting additional constraints in to make fabrication or reliability better? So maybe that you don't want to change refractive index faster than a certain rate, and very similar to this.
We haven't gotten to that point yet. It's mostly just, okay, don't give me 1 nanometer host. There is a group in Canada who I think are doing, actually, okay. They're not playing with the rate you're changing the refractive index, but they're doing the fabrication tolerance a bit more sophisticated than we are doing. They actually characterize the output of their EBL machines. So they know, because anyone who has worked with an EBL? No? You have worked, okay. It's a huge beast. I call them our moody EBLs because sometimes they work well, sometimes they don't work well. But anyway, so they made a database of all the fabrication runs from their EBL, so they get a better idea of their fabrication characteristics, and then they put that on the inverse design software that they have. They don't use spins. I think they have their own package. We use the Stanford one from Yelena Vukovic's group.
Please, there is a microphone around somewhere. Someone has the mic. They're not as loud as we are.
Yes, they haven't taught first year physics.
Yeah, so you showed some grating couplers.
Yes, we have grating couplers, yes.
Efficiency is highly dependent on the facial modes. Did you have to compromise for the efficiency, or?
Our grating couplers at the moment are all just accepting single mode, like just all TE0. And they're not inverse design, our grating couplers, like you can sort of work out the efficiency, although there are inverse design grating couplers as well, which vary the periodicity of those slices. I think Tidy 3D would do that for you.
We had it working well.
Hello? Okay. So I was more interested about the reverse engineering. So if I understand, you just design the pattern and you print it as it is, and it worked perfectly the first try?
Yes. So we define what is the function of the device.
Yeah.
Okay, so say send TE0 to this port, send TE1 to this port. And then we give the algorithm a 3x3 area of silicon. It gives us this wild looking pattern, and we just go to the EBL and actually fabricate that.
Okay.
Yeah.
So I suppose it can work with any materials.
It is agnostic to material because when you just, the material is just the refractive indices.
And is there on this software or other software some way to, for example, designing gravity to improve for example, the concentration of the field in a specific region?
They're probably there. So this one is more for like linear optics kind of devices. Like when you have cavity, like there's some, like I don't know what your cavity is, but there are some inverse design techniques as well for cavities. I haven't tried it here with spins. There probably is. Like I've seen some papers.
Okay, so it's impressive.
Yeah, no, I was very surprised. I was very surprised. I asked the student, can you check? Can you check? Can you check again? But yeah, it's...
You need to ask student for one more line.
One more line.
Before they graduate.
And just how this design compares to the best design currently available in terms of photon loss and precision? Are they better or?
I mean, it's comparing apples to oranges, really, because the dimensions of, if you talk about loss, for example, the longer your device is, the more likely you will lose your photon.
Yeah.
Because I have a small device, like of course the loss here will be better. So I kind of feel like it's cheating if I compare this small device to this longer device, right? In terms of loss, but if you're talking about performance like transmission and crosstalk, for example, which is important for multiplexers, we are approaching, if not better in some cases, to like what you design from bottom up, like those techniques where you actually define the width of the waveguide, the bend, the distance between the waveguides. We're not doing worse. If not, we're doing maybe even better than those, and we have smaller footprints.
And okay, so my next question is, so sorry if I didn't quite understand, but are these software publicly available?
Yes, so Stanford software has two versions. Spins B is free. Spins, which is what we have an academic license for it, like it's not expensive. And they're actually very similar. Like spins just have a nicer, like it's just more convenient to use because it's easier to just input your parameters in your YAML file, and but at its heart, I think they're the same. They actually have, they've formed a company now, so maybe they even have a better software now, but we still use spins. That's what I have in the cluster at UQ.
Okay, and in terms of calculation time, for example, if we have a workstation that can sit on a desk, is it enough or is it?
So the first time that we ran it, like the multiplexer design that I showed you, that was on I think my student's laptop. She said it's 8 hours for that. We have tried it in the HPC cluster and it's actually quick, like less than an hour. If that.
The parallels is very, very.
Yeah, it's with a GPU cluster, like you can go wild. What do you want your device to do? Like you want to sort modes, frequency, like you can really be wild with the cluster. So I mean, with the computing cluster, not the cluster state. That's hard to generate.
So one of the things that you can do is you start with the standard design with specify your 3 centimeter by 3 centimeter get something that's good, and then ask it to go back and now make it 2.5 centimeters, 2.5 centimeters, or 2 by 2, and see whether.
Oh yes, actually, that's one thing. Like, why did we choose 3 by 3? Nah, we just
The useful format.
we just said 3 by 3, but you know, no one tells you can't do it with anything smaller.
Okay, and no, I think it's the question I have.
Yeah, there's also work from Stephanie Barz's group in where is Stephanie Barz? She's somewhere in Germany. She also uses inverse design for multiphoton interference. She had an archive maybe 1-2 months ago where she actually showed multiphoton interference, like our visibilities are much better, but they have multiphoton interference. They put 4 photons, I think, on an inverse design network, and they get like, I think 80, 70, 80, I want to say 80% visibility for a multiphoton experiment. We would have tried multiphoton if I had multiphotons, but we only have 2 photons, so. Yeah. Okay.
Thank you very much.
Thank you.
For on chip, like, is there any way to do some sort of like hyper entanglement, like have higher degrees of freedom, or is that just not possible because?
I think it is possible. So actually, I tell you what, I don't think I will make a photonic quantum computer in my lab. That's not my dream. I want to help make one. If I can help make one, I will. Maybe try to discover some encoding that will be useful. But I think we can explore more the foundations, quantum foundations on chip more easily. Like the moment I saw the Zeilinger experiment with the 3 by 3 by 2 entanglement with a 4-fold coincidence of 1 per minute, I said to myself, I think I need more sources. I think I need more sources. And the only way I can do that is to go on chip. And so I go on chip because I think you can do more foundations. You can have higher dimensions. Maybe the dimensions, there's a trade-off between the dimension on chip and on free space. But it's an engineerable thing. So I want to do foundations. I think you can use it for some simple information processing. Like if you're talking about some sensing application, I think you can use that as well.
Because yeah, like with those modes, right, like the T modes, you can't do the same thing as you can do in free space, right, where you have maybe like the spatial part and the polarization. You can't separate that, right? Like there's no way.
You can maybe you can design devices that maybe can separate it.
Okay.
We haven't tried. Like from a photon source point of view, you can have spontaneous 4-wave mixing on chip that will support more modes. So in fact, we have simulations actually with, I think 4 or 6 modes, I don't remember. And we have actually started to measure coincidence to accidental ratios using inverse design multiplexers, and we are really getting good GAR values for the 2-mode ones. So our 2-mode spontaneous, spontaneous 4-wave mixing with the multiplexers, inverse design, are actually beating some of the really good cars from other traditionally designed multiplexers and spontaneous 4-wave mixing.
Thanks.
Yeah.
Any further questions?
If not, it's lunch.
No.
Oh no.
Appreciation of,
Oh, thank you.
and we thought you needed one for the ride.
Okay. Thank you.